Today we will be talking about P and NP. Now, what are decision problems? Decision problems are the set of all problems whose answer is an yes or no. For example, suppose we are trying to run a search algorithm where we are asking whether the element 5 is present in the array or not. So the answer to this question is either yes or no. So the searching problem is a decision problem. Another example is if I ask a question, is there a spanning tree of graph G whose weight is less than 10? So this is also a decision problem because either the minimum spanning tree of this graph is less than 10, in that case the answer is yes, otherwise the minimum spanning tree of this graph is more than 10, and in that case the answer is no. So there is another category of problem which is known as optimization problems. Now optimization problems are problems where we are interested in finding the minimum or maximum, like finding the shortest path between two vertices, finding the minimum spanning tree of a graph. All these are examples of optimization problem. Now there is a very interesting fact, that is, if we know the optimization solution of a particular problem, then the corresponding decision problem can be easily obtained from that optimization problem and vice versa. For example, if we have an algorithm to find the minimum spanning tree of a graph G, say its weight is 10, now if somebody asks me, is there a spanning tree of graph G whose weight is 8? From the optimization solution, I can directly give an answer to the decision problem without requiring another algorithm. I will directly say that the answer is no. Similarly, if we can devise an algorithm which can answer the question, is there a spanning tree of graph G whose weight is x? So for example, in our previous example, if we were to test with the same graph, if is there a spanning tree of graph G with weight 1, the answer to that will be no. We will then check with weight 2, the answer to that will also be no, and we will go on doing this until we check with weight 10, the answer to that will be an yes, and we will say that the minimum spanning tree of this graph has weight 10. Now from these two examples we can see that for every decision problem there is a corresponding optimization problem, and for every optimization problem there is a corresponding decision problem. The solution to one helps us to obtain the solution to the other. As optimization and decision problems are equivalent, in our discussion today we will only deal with the decision problems. So the first and the most important decision problem is the Boolean satisfiability problem, or the SAT problem. It is a problem where, given a formula, we have to check whether it is satisfiable. A formula is satisfiable if we can find a combination of input for which the formula's output is 1. For example, say the formula is A dot B, and if I now ask the question, is this formula satisfiable? That is there a combination of A and B for which our formula will be 1? In case of A dot B, the answer to this question is yes or true, because for A equal to 1 and B equal to 1, A dot B is equal to 1. But if the formula is A dot A dash plus B dot B dash, then the answer to this SAT is false, as there is no combination of A and B which will result in the output being 1. Hence, A dot A dash plus B dot B dash is not satisfiable. What is the easiest way to solve the SAT problem? We could draw a truth table taking the logical formula and check if output of any row is 1. If yes, we say it is satisfiable, else we say it is not. So how much time will this procedure take? We can build a truth table, and if the input formula has n variables, then the number of rows in the truth table is 2 to the power n. Essentially, the problem becomes an exponential problem. Now, what is a verifier algorithm? If an oracle gives us an answer and we can verify to check whether it is correct or not, for example, we can say, for example, in the SAT case, if somebody gives me an answer, say if somebody tells me for a equal to 1, b equal to 1, a dot b equal to 1, then I don't need to search for the combination for which it is true. I can verify it directly by substituting it in the formula, and in that case I don't need to search for the 2 to the power n options. So a verifier algorithm does not find the answer, but it only verifies whether the answer given to it is correct or not. Now, what is NP and P? A problem X is in NP if given a solution to X. If somebody gives us a solution to X, we can verify whether the solution is right in polynomial time. Like in the satisfiability case, if somebody gives me an answer, I can check whether the answer is correct or not, or whether the answer satisfies or not by substituting the value in polynomial time. Hence, satisfiability is in NP. Now, a problem X is in P if we can find a solution to X and also verify whether the solution is right in polynomial time. Like, for example, the linear search problem, where we can find the solution and also verify the solution is correct in polynomial time. Now, what is polynomial reduction? A reduction from problem X to problem Y means that if we have an algorithm for problem Y, we can use it to find an algorithm for problem X. It's a polynomial time reduction if this can be done in polynomial time. Let us take an example. So, let us take a graph with the set of vertices denoted by V and set of edges denoted by E. A set of vertices X, subset of V, is called an independent set if no two vertices of X are connected by an edge of G. It's called a clique if every pair of vertices in X is connected by an edge of G. In the figure given below, the red vertices denotes an independent set as those two vertices are not connected by any edge, and the blue vertices denotes a clique because every vertex is connected to every other vertex. So the set of blue vertices is a clique, the set of red vertices is an example of independent set. Now, what is an independent set problem? In an independent set problem, we are given a graph G and an integer k, and we are asked to decide whether G has an independent set of size greater than equal to k. In our previous example, we see that the size of independent set here is 2 and the largest clique is of size 3. So, an independent set problem asks you a decision question that whether the graph has an independent set whose size is greater than equal to k. Similarly, a clique problem asks you a question given a graph and an integer k to decide whether G has a clique of size greater than equal to k. So for our previous example, we can see that if I ask the question whether this graph has a clique of size greater than equal to 4, the answer to this question will be no. And if I ask the question that whether this graph has a clique of size 3 or less, the answer to this question is yes, because it has a clique of size 3. So, what do we actually do in reduction? For decision problem X and Y, a reduction from X to Y is an algorithm that takes an instance of X as input and returns an instance of Y as output, such that the solution yes and no to IY is the same as the solution to IX. So, let us see how we can change the independent set problem to a clique decision problem. We convert the graph G of the independent set to a graph G dash, in which for every edge u comma v, if it is not in G, we introduce that pair u comma v in G dash. That is, G dash is the complement of G. And on G, we ask the question whether there is a clique of size k in G dash. If the answer to this question is yes, then the answer to the independent set question is also yes. So we have reduced the independent set problem to a click decision problem. Now if we have a solution to the click decision problem, we can use that solution to also give an answer to the independent set problem. So independent set can be reduced to click. What it means is that if we have an algorithm for click, then we have an algorithm for independent set. Click is at least as hard as independent set. Also, independent set is at least as hard as click, which essentially means that click to solve the click problem is at least as hard as to solve the independent set problem. Now, what is the definition of NP hard? A problem X is NP hard if every problem Z in NP reduces to X in polynomial time. So, if I can reduce every problem in the set Z to a problem X, then that problem X is known as a NP hard problem. Example is satisfiability problem. Now this is very intuitive. See, satisfiability problem means a logical formula. Now every problem can be represented as its logical formula. So if we can find a solution to this logical formula, we can also find a solution to the original problem. Hence, every problem in NP reduces to a satisfiability problem. Hence, satisfiability problem is an NP hard problem. Now, once we have an example of satisfiability problem, we don't need to reduce every problem in NP to find another problems in the NP hard set. What we can do instead is just reduce the satisfiability problem to that problem X. So an alternative definition is a problem X is NP hard if satisfiability reduces to X in polynomial time. Now what is NP complete? A problem is NP complete if it is NP hard and it is also in the set NP. So the definition of NP complete is a problem X is NP complete if every problem Z in NP reduces to X in polynomial time and X is itself in NP. Again an example, satisfiability problem. Now there is an alternative problem which is NP hard but not NP, that is the halting problem. So satisfiability reduces to the halting problem, but halting problem is not in NP. Thus halting problem is in NPH but not in NPC. So what is the halting problem? The halting problem is given a word to a Turing machine, whether the Turing machine will halt on that word or not. Now see, even if I have a verified algorithm where I say that this word W will halt in a Turing machine, it is not guaranteed that I will get the solution to that in polynomial time. So halting problem is not in NP. Hence halting problem is in NPH but not NPC. So what is Cook's theorem? Cook's theorem says that if satisfiability is in P, then P is equal to NP. What it means is that if we can find a polynomial time solution to a satisfiability problem or any of the NP complete problems, then all problems in NP can be solved in polynomial time. So this is the final P versus NP graph. If we are able to find a solution to the satisfiability problem, a polynomial time solution to the satisfiability problem, then the Venn diagram will look like the right hand side. Then P, NP and NP complete will all be the same set, whereas NP hard will be a set which comprises of NP complete and NP hard. The extra part will contain problems like the halting problem. And if P is not equal to NP, that is we are not able to find a polynomial time solution to the satisfiability problem, in that case the graph will look like this, that P will be a subset of NP and NP complete will be the overlap of NP hard and the NP set. So this is the reference algorithm designed by John Kleinberg and Eva Tardas. Thank you.